All right, happy Friday, everyone. Glad you could join us today. Let's pick up where we left off the other day. So, the other day, I put up a really ugly, intimidating looking structure. All right, so I'm going to redraw it up here. We saw what happens whenever you take a cyclic diene and put it in a Diels-Alder reaction. All right, so the one we put up was basically the simplest one of this type that we can have, right? Cyclopentadiene. The mechanism we said works exactly the same as any other Diels-Alder reaction. You form a new six-membered ring, but you don't actually break the other ring. So we said he created something called a breached bicyclic compound. Right, so I'm going to redraw this product. And just point out a couple of things to you that maybe will make this seem a little less intimidating. It's actually pretty intuitive when you think about it. The reason this is the preferred way of drawing a structure whenever you do make a breached bicyclic is because it's a lot easier to sort of show the fact that you actually have two separate rings, right? You have this six-membered ring here. I want to do the thing where I label the carbons again. Okay, so you can really signify the fact here that you made the new six-membered ring between the four carbons, A, B, C, and D, of your diene, right? They're always going to be located here, 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 and here. Those four carbons. X and Y always come from the dienophile. They're always the one over here on the far right side, right? The two new sigma bonds that you make are right here and right here. All right, so it's a very predictable pattern. It's basically the same things that you look for every time. There's just a few little things that could change, right? E represents the leftover carbon or carbons from your original ring, right? This is called a bridgehead carbon. Because literally it's sort of acting as a bridge between carbons C and D. And when you do it like this, it's a little bit easier to see that individual carbon kind of poking out and the fact that this five-membered ring is in a central plane. Alternatively, you'd have to draw it like this, which number one, in and of itself, I think it's a little bit harder to see the two individual rings than it is up here. And number two, these structures can get more complicated, and you'll see that this gets a lot harder to draw. Okay? Now, you can do this with other size rings too. You can do this, with a six-membered ring at the beginning, right? Six-carbon conjugated diene. And really, you see, not much here is changing, right? We're still using the same four carbons from your diene and the same two carbons from the dienophile. Oops. Right, to make the six-membered ring. What's the only difference between this one and the last example? Yeah, you're going to have two bridgehead carbons here instead of just one, right? So instead of just drawing a little point like that, you need to make sure to draw something more like that to represent the fact that you had these two carbons. If you had a 7-membered ring as your diene, how would that change it? 3, yeah. Theoretically, I mean, you could keep going, 8-membered, 9-membered. Beyond 7, you're really not going to get very stable though, so you're not going to really see any of this. But it is possible to have like one of these with a bridgehead of 1, 2, or 3 carbons.
On the right side, like technically with the double bond between B and C, like label it.
Did I just label it wrong? Yeah. Oh, no!
It would be A, B, C. Next to the X.
Yeah, yeah. Hold on. My numbers or my letters are wrong. All right, so let's see. X connects to A. Yeah, so A should be over here. B, C, D. Thanks for catching that. Otherwise things could get pretty confusing. Any questions so far? All right. Now, one thing that you'll see quite often is that you'll have something hanging off of your diene file. And there's actually a lab that we're going to do. We're going to do Diels-Alder reaction in lab next week. And we're going to be using we're going to be doing an example like this where we have a cyclic diene and then a diene file that's going to have substituents hanging off it. And there's a little bit of stereochemistry that comes into play. All right. Let's say you had cyclopentadiene and you reacted it with this. I'm going to put an ester group hanging off of your diene file. All right. Now, again, this is very formulaic. It's as far as drawing the basic structure goes, right? Mechanism's the same. Merry-go-round of electrons. It's a cyclic diene, so in your head, you should probably think automatically, just go ahead and draw this little basic framework over here. It's a little awkward drawing it first, or now, as I just screwed it up. But I think it's easier than chair conformations, to be honest. 6 carbons of your 6-membered ring. Your double bond goes here. How many bridgehead carbons do we have? 1. So draw your bridgehead. And so we've got everything here except for this ester group that's hanging up. Yes? Is there a group off that one? Yes, sorry, that's a methyl group. I don't know if I probably didn't draw that clear enough. There we go. All right. So we're going to have an ester group hanging off of this carbon. There's a couple of different ways you can draw it. You could draw it like that. Or You could draw it like that. Does that bring anything to mind? Does that look familiar at all? What does that bring to mind? Or what horrors does that bring out of your subconscious? What's that? Yeah, it reminds you a lot of axial equatorial from chair conformations. So guess what we call these? Not axial and equatorial. You'd think so, right? Yeah, I don't know. Those fellows at the IUPAC are tricky. We actually have a different term for this, right? If it's pointed straight down off of your Diels-Alder product, we refer to this as being in the endo position. If it's pointed out at an angle, the one that's sort of similar to equatorial, that's called the exo position. Right, so there's a little bit of different terminology. Which one's better? Which one's more stable? Which one's more easy? Which one's easier to form? Or are they the same? Well, think back to chair conformations. Generally speaking, whenever you had a substituent group, was it more stable in the equatorial or axial position? Equatorial, guess what? It's going to be the opposite here. I know, right? Oh, you got to love these conflicts. The dominating factor with chair conformations was steric hindrance, right? We said if it was in the equatorial position, you know, sort of like exo, it was less crowded. That actually is the same thing here. You get more crowding with this, so that's bad. But as it so happens, to go through the transition state of this, having one of these groups in those positions actually helps to stabilize it electronically. I'm not too worried about, you know, you guys knowing the explanation for that or anything, but I just wanted you to know there was a reason, right? And that stabilization of the transition state is more powerful than steric effects here. So, bottom line, whenever you have a choice, the endo position is preferred. So if you did this reaction, you would get this compound, you would not get that. Yes, ma'am.
So the endo is preferred. Is there a way we get exo instead?
Excellent question. Is it possible to even get anything at exo? Yes. Yes, it is. I'm about to show you a couple of examples here. And we're going to see in one of them how we can get exo, something in an exo position. All right, let's try another one. We'll go with cyclohexadiene this time. We're going to use a dye-substituted diunifier. All right. So we're going to have two substituents. All right, draw your framework, your skeleton. Yeah, if you see a cyclic diene in a Diels-Alder, just automatically go to this. All right, this will always be here. How many bridgeheads are we going to have? I have two. Draw your two bridgeheads. And we're going to have two ester groups. One on each of the carbons that used to be in your diunifier. Right? Now, what do you know about these two ester groups relative to each other? There was a rule we learned. What's that? Yeah, we learned that you want to preserve stereochemistry, right? So these two guys have to be on the same side. That means they could both be in the endo position or they could both be in the exo position. Which one's going to happen?
Exo.
What's your second choice?
Endo.
Yeah, endo is preferred, right? So we can make the cis product here. Crowding a little bit, so forgive me for also crowding against my artificial border. Hopefully you can see that. But they're both in the endo position. So this one's doubly happy, right? It gets to preserve stereochemistry of the dienophile, and it gets to put both things at the endo position. Yes, ma'am.
So with endo, is it always gonna go like point down or can it point up?
If you draw this framework over here, it'll always point down. All right. Any other questions on this one? All right, let's tweak it a little bit. Same thing, but we're going to start with a trans dienophile. This kind of throws a bit of a wrench into things because in the last example, you saw that everything agreed. All the requirements, whatever, they agreed with each other. Here, though, first let me draw the framework. Here, it's a little bit of conflict. Where's the conflict? On one hand, what do you want to do with regard to stereospecific? Yeah, cannot talk today. Stereospecificity. Yeah, they're trans in the dienophile, so you'd like to have them trans or opposite in the product. Now, in order to put them trans in the product, what does that mean as far what we'd have to do as far as endo-exo? We'd have to have one endo and one exo, right? So that would mean we would violate the endo-exo rule. So somebody's not going to be happy here, metaphorically. They don't actually have personalities that I know about, right? So which one do you think we're going to hold to? Who says we're going to stick to the cis-trans requirement? A few very tepid yes votes. Who thinks we're going to stick hard to the endo rule? Again, a few very tepid yeses. So you have no way of knowing, so until I tell you so. It's basically just a blind guess. Well, there's one in the endo position. Where am I going to put this one? It's going to go exo. The rule about stereospecificity trumps that of the endo-exo. You always, always, always have to respect the stereochemistry of the dienophile, even if it means putting something at an exo position. So, Marissa, that is how you get something in an exo position, right there. Is when the stereospecificity, I cannot say that word, stereo, that's a really hard word to say. Say that 5 times fast. Stereospecificity is, yes. No, no need to do dash wedge. It's just like the axial equatorial. You know, they're represented by just plain lines. Yep.
So if we had to say like, is it endo or exo? So for this molecule, would we say it's endo and exo, or would we specify like a certain point it's endo, a certain point it's exo?
Yeah, if you were going through and naming this, which we're not gonna go over that, but yes, you would have, if you were gonna, you'd have to say like, you know, 5 endo or 4 exo or whatever, corresponding to carbon number. There's a different series of nomenclature rules, by the way, for bridge bicyclics. They involve, you add brackets and periods. So we're not going to bother with that. Yeah. No. Oh, you good? Change your mind? Okay. All right. Does that make sense? Are there any questions so far? All right. Getting a few questions this morning. I like that. Very cool. All right, so let's see what's next. Oh, there's a related reaction. Called the retro-Diels-Alder reaction. When you hear the term retro, what does that mean to you? Kind of going back in time, right? Any of you into retro stuff? Retro music, retro fashion, retro gaming? Like, no, that crap's for old people. I like retro gaming, but don't get them old. But yeah, you're right, backwards. A retro-Diels-Alder reaction is basically a Diels-Alder reaction in reverse. In other words, you start off with a Diels-Alder product and you revert to a diene and a dienophile. And one thing that's a little confusing about these is that just like Diels-Alder reactions, they're thermal. So you input heat. However, the heat that you add is more than a traditional forward Diels-Alder reaction. When we say heat for Diels-Alder, regular Diels-Alder, sometimes that just might mean room temperature heat, right? 25 degrees Celsius or something like that. And crank it up to high temperatures, like say, 150 degrees Celsius or something, that's going to more cause things to decompose. And that's basically what this is. It's a decomposition of a Diels-Alder product. All right, so let's say we have, this guy. Literally what you're doing is you're making the diene and dienophile, and therefore you're sort of running the merry-go-round of electrons in reverse. First of all, I'm going to fix my hexagon because it looks ugly. Gotta have sharp corners on it. There we go. All right, so you remember when we did Diels-Alder, we said we broke 3 pi bonds and we formed 2 new sigma bonds and 1 new pi bond, right? This is the opposite of that. Let's look at this and identify the sigma bonds that we're probably going to break. All right, again, I'm just going to label these. A, B, C, D, E, F, right? Which bonds are we going to break here? You guys tell me. Do you see any sigma bonds that we would break? What's that?
A and D.
There is no sigma bond between A and D.
Sorry, B, C. I'm lost.
It's actually not going to be between D and C.
A, D, E.
Yeah. These 2 right over here are going to be broken. Always remember, 2 of your carbons came from the dienophile, the other 4 came from the diene, right? The 2 carbons from your dienophile have to be connected. So this sigma bond's going to break. The electrons are going to go over there. This pair of pi electrons will form a double bond between A and B. And now this bond between A and E will break, and those electrons will form a pi bond between E and F. And you have retro-Diels-Alder products. Okay. Now, you can have other stuff attached here, right? But honestly, it works the same no matter what your hexagon is. You're going to be doing the reverse merry-go-round in the same order. You just might have some extra stuff sticking off of those carbons. All right. Seems a little bit more intimidating. If you do it with something like this, one of these, then it's still very predictable. All right, so let's say we did a retro Diels Alder reaction for this particular product. Again, let's label the carbons. A, B, C, D, E, F. Let's just say G and H here. All right. Well, which sigma bonds are going to be the ones that we need to break?
G and D and H.
What's that, Marissa?
A and G, D and H.
Between A and G and D and H. Yeah, exactly. And so once you figure that out, you can break D and H. Those electrons move to form a pi bond between C and D. This pi bond can shift over here between B and A. And this sigma bond breaks. You can form a double bond between G and H. All right. So then we have two bridgehead carbons. So that means our original diene had 6 carbons in it. Our dienophile had 2 aldehydes. Are those aldehyde groups cis to each other or trans to each other? Cis. Because they're on the same side. They were both endo here. That is it. And you'll get that. Y'all see how we got that? Are there any questions of how we got that? I'm gonna put one more up here. I'm gonna have you guys do it. Let's see if you did it right. This is one we're actually going to be working with in lab. So you guys are going to be doing a retro Diels Alder reaction as part of your experiments next week. You're going to love this structure. Ooh. Yay, another ring hanging on. All right. Still workable, very, very easily through the same processes. Sketch through that real quick and see if you can figure out the retro Diels Alder products. All right, looks like several of you have finished. Tell me, what did you get?
Cyclopentadiene for the first part.
Okay. So how'd you get cyclopentadiene?
There's a magnetic field for
Yeah, we got a 1 carbon bridgehead. Again, these two are going to be the sigma bonds that you're going to target, right? So you're going to move a pair of electrons there, pair of electrons here, pair of electrons here. So yeah, I can definitely say that you will get cyclopentadiene. So you said that was your first product? What's your second one? What's that? Cyclopentene?
Isn't it the same thing? Is this cyclopentadiene?
Yeah, you end up with 2 molecules of cyclopentadiene. Yeah. It's pretty cool. The lab we're going to do is 2 parts. First, we do a retro-Diels-Alder reaction because we want to make a bunch of cyclopentadiene. And then we're going to react cyclopentadiene with a different dienophile. So I'm excited. Yeah, unreasonably so. I will tell you, this is one of our most successful experiments as far as yield. You know, I could just see the defeat in some of your eyes this week. Doing all that work and getting like, you know, what, 3 mils of something. This one gives you a big plate of white crystals. So it's kind of much more just, you know, satisfying. So you usually get like 80-something% yield. So give you something to look forward to. All right. All right, any questions about Diels-Alder or retro-Diels-Alder? All right. That's all the reactions in this chapter. There's just one more little thing I want to talk about. I want to revisit the whole idea of conjugated systems and absorption of light. So I want to highlight something, again, another real world type of thing here. All right. I'm sure all of you are familiar with sunscreen, right? You guys use sunscreen?
Yeah. Sometimes.
I heard a very clear no from somebody. I don't know who that was. What are sunscreens used for? To block harmful ultraviolet rays. All right. So a little bit more about UV. There's 3 different categories of UV light. There's UVA, UVB, and UVC. All right. As we go down the list, the wavelengths get shorter. I actually forgot to write down my note for UVC, so give me a second. Yeah, okay. So if we're looking at wavelengths, UVC is less than 290 nanometers. UVB is 320. Oops, excuse me, 290 to 320. And UVA is 320 to 400. Which ones are the most harmful ones, do you know?
Shorter.
Yes, if you remember anything about the electromagnetic spectrum, shorter wavelength equals more energy. So UVC are the most harmful ones. However, these are mostly filtered out by the ozone layer. So you can really see the importance of the ozone layer, right? It shields us from the most harmful UV rays of all. But UVA and UVB, they have more of a tendency to get through because their wavelengths don't tend to be absorbed by the ozone layer quite as well as the wavelengths right here. So that's where we rely on sunscreens. Most important with UVB, because obviously shorter wavelengths, more energy, UVB rays are what tend to give you sunburns. UVA rays generally don't have enough energy to give like concentrated sunburns, but they can cause damage to cells over a long period of time. So it's still important, even if you're just shielding from UVA rays, to wear sunscreen, especially if you're very sensitive to light. So if you're looking at sunscreens, they're going to have active ingredients. Anybody know the common active ingredients in a sunscreen? What's that? I heard somebody say something. What's that? Zinc oxide is used, but it's not what I'm thinking of. That does help you, but not through conjugation. I know you put zinc oxide on your nose a lot. You guys ever heard of PABA? Look at your sunscreen bottle next time. You'll see something called PABA. It stands for para-aminobenzoic acid. Right, that is para-aminobenzoic acid. That's PABA. That is the most common active ingredient in most sunscreens. And you can see, if you're looking for conjugation, we definitely have a conjugated system in here, right? All of those atoms that I just circled are conjugated. So you basically have a system of 1, 2, 6, so 8 atoms that are conjugated, right? What happens to the absorption of wavelengths as we increase conjugation? As we increase conjugation, do we absorb shorter wavelengths, higher wavelengths? What? Go back and look if you have to. When we were talking about lycopene and beta carotene. Yeah, more conjugation equals higher wavelengths. So we said that most organic compounds absorb at very low wavelengths in the ultraviolet region. By sort of targeting a semi-extended conjugation range, sort of like this one, you can model your molecule to absorb specifically within this region of ultraviolet. This is still colorless, right? We still can't see it, a color to it, because it's not in the visible range, but it still absorbs a little bit longer within the UV range compared to most other organic compounds. As a result, this will take the bullet for us whenever we absorb or whenever we are hit with ultraviolet light. If you have it on there, it'll react, or it'll be absorbed by the PABA and not your skin. There's another one that's commonly used. Looks like this. This is called Patamate O. Where they got the name from, I have no idea. But it's called Patamate O. But it's another common ingredient in sunscreens. And again, you'll see the core conjugation system is basically the same as PABA. Right? So this is sort of the happy zone here of conjugation that can help to absorb the light, but yet still be mixable in a formulation and blah, blah, blah. So I'm sure as you've been laying out on the beach, you've been wondering to yourself, why do I not get sunburned when I put the sunscreen on? I'm sure you'll think about that next time. This is why. Everybody knows what SPF is, right? Or has heard of SPF? What is SPF? You know what it stands for? Sun protection factor. You have SPF, what, 20, 30, 50, 70, it gets higher and higher. You know how you increase your SPF of a sunscreen? You increase the concentration of this stuff. That's all it is. That's what causes something to have an SPF that's higher than another. You just simply have more of the active ingredients in there. I've heard that it really doesn't make much of a difference between once you get beyond like SPF 30. I don't know. I'm extremely pale, so you know I generally play it safe for whatever the highest one I can find is. Oh, which leads me to another thought. Are you guys familiar with melanin? What is melanin? Everybody says yes. What is melanin? On a base, what's that? Pigmentation in the skin, right? You know, people have different different shades of skin, right? Some people are very, very light colored, some people are dark colored, some people are in between. That's all due to the concentration of a compound called melanin. And there's actually a few different types of melanin. I forget, I'd have to go back and look. But one type of melanin is responsible for like more like just regular skin tone. Other is specific for like pink and red skin tones. One type is responsible for giving you black hair. Another type is responsible for giving you red hair or blonde hair. And different concentrations can give you like brown hair and like what you call sort of the salt and pepper type hair when you get old, right? Melanin, all different types of melanins are highly conjugated, right? So that's why, you know, people's skin or hair tends to have different shadings, because different concentrations of these conjugated species will absorb, number one, at different wavelengths of light, and also to different degrees, right? And also people with higher concentrations of melanin generally tend to be a little bit more resistant to UV rays. Not completely resistant by any means, but a little bit more resistant. So for some people, it's easier to sunburn than others. You put me out in the sun for 5 minutes, I will be probably red as a tomato. Other people, I mean, I may be exaggerating a little bit. Marissa, your eyes got really big there, so like, yeah, I don't want to freak you out. But other people can go into the sun and, you know, for 2 hours and, you know, not have to worry about a sunburn or anything. So it's all a little bit different. But it's all due to the conjugation of, the particular conjugation of the melanin that you have in your skin. Have you guys talked about that in genetics yet? I think I did this one year, and like I was talking about this the same time that genetics people were talking about it from a genetics point of view. No? Okay. Give you something to look forward to. All right. That ends the chapter on conjugation. We're not done yet, so don't get too excited. Are there any questions with regard to conjugation resonance dienes before we move? All right. Well, the next 2 chapters are going to open up your OChem world. I know you're thrilled about this. You're about to experience a magic, wondrous ride to the field of aromatic compounds. Yeah, you guys don't give a shit. We're going to try to change this. All right. No, in all seriousness, all right, shh. In all seriousness, we have talked a little bit about aromatic compounds here and there, kind of mentioning them. We talked about them in IR spectroscopy. We've mentioned them here and there in other contexts, but we haven't really explored them yet. Chapter 17 sort of gets our feet into the water, learning how to recognize certain types of aromatic compounds. And then chapter 18 is a really long chapter that looks at reactions. All right. What we're going to see about aromatics is that they are very different from a lot of the other things that we've studied, even though, you know, some of the appearances are pretty similar. They do different things. All right. Well, let's start off with the most common, well-known aromatic compound. Is this. This is benzene. All right. Benzene. Now, if you look at benzene, you may or may not wonder why it's called benzene. Looks like we should be able to call this like 1,3,5 cyclohexatriene, right? Well, the reason we don't do that is because even though, yeah, this looks like it has alkene groups in it, it doesn't behave like an alkene or, you know, a diene or triene or whatever. For example, if we did this, right? This is from the alkenes chapter. See how much you remember. If we added an alkene to HBr, what would happen? What type of reaction would you get? Addition, substitution, elimination? What's that? Well, let's go through the mechanism. HBr, strong acid. What do strong acids like to do? Wow, you guys got really quiet all of a sudden. Strong acids like to, what's that? Dissociate, and when they dissociate, they give off hydrogen, protons, yeah. So H plus is going to come off. Where's it going to go? It's going to go to one of the carbons in the double bond. Markovnikov's rule is going to state it's going to be that one. Makes a carbocation. Br minus adds. And boom. That's an addition reaction, right? We're adding HBr to the double bond. We could take benzene, add HBr. Guess what happens? Not a darn thing. No reaction. That's different. Benzene does not undergo addition reactions like a traditional alkene would. Yeah, so you can see, you know, the types of things that we're going to be looking at here are going to be very different. Why wouldn't it? Why wouldn't, you know, benzene want to add HBr to a double bond? Well, there's a good reason for it. The reason benzene doesn't want to do this is because benzene is already a very stable compound. It's happy the way it is. Any guesses as to why it's so stable? It is highly conjugated, yes. So yeah, absolutely. We look at benzene. It's got sp2 hybridization of every single carbon. So the whole thing is conjugated. That means those 6 electrons, they can all swirl around that entire ring. We can also visualize this in terms of resonance. Yeah. You can draw a crap ton of resonance structures. I'm going to draw one additional one right now. All right, let's say this pair of electrons moved over here. This pair of electrons moved over here. That pair moved over there. That would be one example of resonance. You could draw other ones too, where like they hop up on individual carbons and give charges and stuff. But this one sort of tells the story. Basically, in a nutshell, these electrons have a ton of space they can spread out. They can circle through that whole molecule. That makes them very happy, right? In fact, we can draw a particular resonance hybrid for this that is turned into probably one of the more common representations. And you'll see me draw this a lot. You can actually just draw a hexagon with a circle in it. That is a very common representation of benzene. All right, we'll pick up there on Monday. We're going to keep with the current quiz structure, so we'll plan for next quiz to be on Wednesday. All right. Hope you guys have a good weekend.
Thank you.
See y'all later.